Hi everyone! Today let's talk about session 3.6, Conditional Probability. A conditional probability is the probability of an event occurring given that another event has already occurred. The conditional probability of an event A occurring given that event B has occurred is denoted by probability of A given B. So this vertical line is read as given, okay? So probability of A given B, it equals, because B has already occurred, so that's why the numerator, we need both of events A and events B occur, but we already know probability B has occurred. So that's why we have P of A and B over P of B. Okay, so this is the conditional probability. We already know that B has occurred. Okay, so that's why is in the denominator, P of B. And because we're asking the probability of A also occurred, so that's why the numerator, we have B and A both occurred. So probability of P, A and B. Okay. Fact, if A and C are disjoint, then probability of A given B plus probability of C given B equals probability A or C given B. Why is that? By definition of conditional probability, this is P of A and B given B has already occurred. This is P of C intersect B given that probability B has occurred. So now, because the denominator is the same, we can just add the numerator, and then A and B plus P of C and B. Oops. Because A and C are disjoint, so that's why we know A and B and C and B, they're also disjoint. Why is that? Okay, think about it. This is A, this is C. They're disjoint, right? If we have another B, then you can see A and B and C and B, they are also disjoint. Oh, this guy looks like a panda, right? Okay, so this is probability of A and C and B over P of B. So that's why, this is OR, okay, A or C and B. And that's why we have this, okay? Example 1. What is the probability of 2 head out of 3 flips of a fair coin, given that the first is head? Okay, so we flip the coin 3 times. And so we flip the coin 3 times. We know the first time is head. Okay, and we're looking for the probability of 2 head out of 3 flips. Okay, so probability of 2 head out of 3 flips. Okay, let's see what's the probability that we get 2 head out of 3 flip, given that the first one is already head. Then we have it could be head, tail, or it could be head, tail, head, right? So this is 2 head out of 3 flips. And how about P of B? So B, okay, so you can see this is like A, this is like B, P of B, okay? The first one is head, and then we get a head, tail, or head, tail, head, tail. Okay, and what is the probability of an outcome? So here we flip the coin 3 times, and each times we have either head or tail, 2 possible ways. So total is 8. Okay, so the sample size of S is 8. Okay, so that because all of them are equally likely, so outcomes are equally likely. That's why the probability of each outcome is 1/8. So now the numerator probability, so this event has 2 outcomes, so that's why the probability is 2/8. And the denominator has, this event has 4 outcomes, so that's why the probability is 4/8. 8 cancel, we get 2/4, which is 1/2. Okay, so the probability of 2 head out of 3 flips of a fair coin, given that the first is head, the probability is 1/2. So far, so good, everyone. Alright, let's continue. Fact. If all outcomes are equally likely and finitely many, then the probability of A given B equals the number of elements in the events A and B over the number of elements in the event B. Why is that? Because remember, by definition of conditional probability, this is P of A and B over P of B. And P of A and B is the size of A and B over the size of the sample space. And the denominator, we have that. So SS cancel. So that's why we get this. Okay? The size of A and B over the size of B. Okay, note. So for P of B greater than 0, then P of A given B equals P of A and B given P of B. And then P of A complement given B is P of A complements and B over P of B. And P of B given B, any guess? B given B, because B has already occurred, so B must occur. So the probability is 1. And you can think of that, this is P of A given B plus P of A complement given B. Right? So that's why we have P of A and B over P of B plus P of A complement and B given P of B. This is, and the numerator, because they're disjoints. So that's why you have P of A and B union A complements and B. And wow, the numerator, because A union A complement, they kind of just a universal set. Intercept B is just P of B. So P of B over P of B is 1. Okay? Alright, let's continue. Theorem. Multiplication rule. The probability that 2 events A and B will occur. Okay, so 2 events occur. Okay, if A occur first, then we have P of A times P of B given A. So this is like A occur first and then B occur. Okay, so this is like A occurs first. And then the other one, it could be like B occur first, so that's why we have P of B, and then after B occurs, A also occurs. So this is like B occur first, then A. Okay? And probability of A and B and C, well, if we can like A occur first, after A occur, then we have B. After A and B occur, we have C. Okay, so to help you to memorize this multiplication rule, okay, I'm gonna call it a nickname, breakfast rule. Okay, so suppose you want to eat some food for breakfast. You need to eat apple, banana, and carrot. So what do? You can eat apple first, And then after you eat apple, you eat the banana. After you eat the apple and banana, you eat the carrot. So it's not like you cannot put 3 things in your mouth at the same time, right? You want to eat one by one. So that's why you gotta eat apple first, or you can eat after you eat apple, you eat banana. You can also choose to eat banana first. Okay, you can choose to eat banana first, and then after you eat banana, you can eat carrots, and then after you eat banana and carrots, you can eat apple. So this is another rule. Okay. So think about this as like breakfast rule. Which one do you eat first? So the conditional probability. Alright, example 2. Draw 3 cards without replacement out of a shuffle deck. What is the probability? The first card you draw is queen, the second one is king, the third one is queen. Okay, now let's see. So the first one is queen, let's call it A. Second one is king, let's call it B. The third one is queen, let's call it event C. Okay, then this probability of A and B and C equals, well, we must draw the first card first, right? So P of A. And then after we draw the first card, we draw the second card. And then after we draw the first and second card, we draw the third card. Okay, P of A. The first card is queen. So we have, how many queens in the deck of cards? We have 52 cards total. And there are 4 queens, right? And then after you draw a queen, because this is sampling without replacement. So after we draw a queen, and then there is only 51 cards left. And how many kings are there? We have 4 kings out there, right? And then after we draw 2 cards, there are how many cards left? 50 cards left. And because the first card you draw a queen, now how many queens left? 3 queens left. So that's why we have the conditional probability. And let's see, what is this? So I need my calculator. So let me move this upper. So 4 times 4 times 3 divided by 52 times 51 times 50. Okay. And, oh, such a small number. So 3.6199. 3.6199 times 10 to the negative 4. Okay, we can also press this button to change to, okay. So usually this button, we can press this and then we can get fractions. Okay, and this one works, but this one, maybe the number is too small, so it won't give fractions. So, but I can tell you the answer is 2/5525. Okay, so this is conditional probability. Alright, and it's really important, especially for the sampling without replacements, because the first round, what we saw, you get the first round really changed your results for the second round and third round. Okay, so example 3. 90% coins are fair and 10% are biased, with probability of getting tail is 3/5. Pick a coin at random and flip. Find the probability of the result is a tail. Okay, what is this? So what is the outcome? Well, here we get the result of tail. It really includes 2 things. First, we're gonna pick a coin and flip, and then the second, we get the tail. Okay? So here, the outcome is not only like getting tail, the outcome also includes we pick a coin first, and then we flip and get a tail. Okay, so now let's define let A be the event of getting tail, and let B1 to be the coin we pick is fair, and B2 is the coin we pick is biased. Okay. Now, we're looking for P of A. Okay, so P of A, what is that? We get tails, but we might pick a fair coin, or we might pick a biased coin, right? And you can see because the coins only consist of two types, so 90% coins are fair and 10% coins are biased. So if I would like to draw a picture, then this is like the relationship. We have B1 and B2. B1 are the 90% coins are fair, B2 are the coins that are biased. And then tail is like here. So P of A, you can see P of A is probability of A and B1 plus the probability of A and B2. Okay, the coin we pick could be fair or biased. So now, after we get this, okay, what is P of A and B1? So pick a coin and get a tail. Of course, we need to pick a coin first, right? So that's why we need to pick a coin, pick a fair coin, so P of B1 first, and then P of A given B1. Okay, plus P of A and B2. So also multiplication rule. Do you pick a coin first or you get a tail first? Of course, you need to pick a coin first. Then you flip the coin and get a tail, right? So that's why P of B2 times P of A given B2. Okay, what is P of B? What is the probability of getting a fair coin? So 90% coins are fair, so that's why this is 0.9. What is the probability of getting tail if we have a fair coin? Well, fair coin, we get 1/2, right? And then plus P of B2, well, B2, 10%, so 0.1 times. If we get a biased coin, what's the probability of getting tail? Well, right here, 3/5. And what is this? Okay, 9.9 is actually 9/10. And this is 1/10. Okay, what is the, let's see, what do we get? Alright, and the common denominator is 100. Okay, here we need to multiply by 5 in order to get that, right? So 5 times 9, 45. Here we want to multiply by 2 in order to get the 100 in the denominator. 2 times 3 is 6. So that we get 51/100, and which is 0.51. Oh, you can also use your calculator. You can also plug this in your calculator and you will get 0.51. So this is the probability of getting tail. So far so good, everyone. Okay, so let's continue. In some probability experiments, the occurrence of one event does not affect the occurrence of another event. For instance, if you roll a die and flip a coin, the outcomes of the roll of the die does not affect the probability of the coins landing on the hat. We call these two events independent. Okay, so given events A and B, event A is independent of B even only if the probability of A given B is the same as probability of A. Okay, what does that mean? Well, it means we really, whether whether B happens or not, it really don't change. Yeah, it doesn't change the probability of A. Okay, so that's why given B happens or B have didn't happen, then probability of A stay the same. Okay, and so theorem. The following are equivalent. If A is independent of B, then B is independent of A. Of course, they're both independent of each other, right? Probability of A and B is going to be probability of A times probability of B. Okay, let's try to prove this. Okay, so first, I'm going to prove statement 1 is equivalent to statement 3. And by the theorem, because by the theorem we have probability of A and B is probability of A, and then it's probability of B times probability of A given B. Okay, and now so if this guy equals to P of A times P of B, it means so then because we have both P of B there, so we can both sides divided by P of B, then we get P of A given B equals P of A. So similarly, if we know this, then we can deduce this. Okay, so that's why 1 and 3 are equivalent. 2 and 3 are also equivalent because P of A given B equals P of A times P of B given A. And if this guy equals P of A times P of B, because we both have P of A, we can both sides divided by P of A, then we get P of B given A equals P of B. So that's similarly, if we have these guys equal, then we can also deduce these guys equals. Okay, so that's why 1 is equivalent to 3, 3 is equivalent to 2, so all 3 of them are equivalent. Alright, let's continue. Remark, if P of B equals 0 or 1, then B and any A are independent. Okay, why is that? Well, let me show you. If P of B equals 0, then P of A and B, because P of A and B is a subset of B, so this guy is going to be less than equal to P of B. And P of B is 0. So P of A and B is 0. So that's why we get P of A and B is P of B times P of A. Because the left hand side is 0, the right hand side is 0 times whatever is 0. So they are equal. Okay, if P of B equals 1, what happened? Well, then P of B complement is 0. Then P of A and B complement is also 0 because it is a subset of the B complement. And then now P of A is P of A and B complement plus P of A and B. Okay, because B complements and B, when we take the union, is the whole universal sets, the sample space. Okay, so that's why, and we have this guy is 0, that's why we just get P of A and B. And, well, because P of B equals to 1, so that's why we have P of A and B equals P of A times 1. So it's P of A times P of B. So this also holds. Okay, so they are linearly, B and A are independent. Okay, and usually when we want to check whether the two events are independent or not, we check the third one, whether P and A and B equals P of A times P of B. Okay, so we usually check this. Okay, check this for independence. Alright, let's continue. If A is independent of B and B is independent of C, this guy does not imply A is independent of C. Okay, so example, we can just pay A to be C. Now you can see A and B are independent and B and A are independent, but the A and C, they're actually the same thing. Okay? Alright, let's continue. Example 4. Flip a coin 3 times. Let A be getting 1 tail out of flip 1 and 2. Let B be the events of getting 1 tail out of flip 2 and 3. Are A and B independent? Alright, so in this case, let's see. Okay, we flip a fair coin. Let's assume it's fair, okay? We flip a coin 3 times. So then as the size of S, so first time 2 outcomes. First flips 2 possibilities for head or tail. Also the second flip and the third flip. So that's why the total we have 8 outcomes. Okay, and so if you want to list all the outcomes, they are like head, tail, head, tail, and then you like can't copy them, but the first one changed to head. That's right, tail. So these are the 8 outcomes. Okay, so the event A, for 1 tail out of flip 1 and 2. Let's see. Not this one. Not this one. 1 tail out of flip 1 and 2. So this one. This one. This one. This one. Not this one. Not this one. So we have head, tail, head. Head, tail, tail. Tail, head, head. Tail, head, tail. Alright, so this is the event A. And then what is P of A? Well, because we have 8 outcomes and all of them are equally likely. They have the same probability. So probability of A is just, here we have 4 outcomes, and then the total we have 8 outcomes. That's why the probability is 1/2. And how about B? Well, B, we get 1 tail out of flip 2 and 3. So not this one, yeah, this one, yes. Not this one, not this one, yes, yes, not this one. So they are head, tail, head, tail, head, tail, head, tail, 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 head. So P of B, you can see we have 4 outcomes and the total is 8. So we also get 1/2. Now, how about A and B? Okay, A and B. So let's say the first one is head, because 1 tail out of flip 1 and 2. So the second one must be tail. And because this guy is in B, 1 tail out of flip 2 and 3, so the third one, it must be head. Okay, if the first one is tail, and then the second one must be head because we get 1 tail out of flip 1 and 2. And because the second one is head, the third one must be tail because we have 1 tail out of flip 2 and 3. So now you can see we have 2 outcomes. So P of A and B is what? 2/8, which is 1/4. Now check. Is PA and B equals PA times PB? Okay, where PA and B is 1/4. Is that equal to 1/2 times 1/2? Yes! yes. The answer is yes. So they are independent. So A, B are independent. Oops. Okay. So this is example 4. So far, so good, everyone. Let's continue. Example 5. Draw 2 cards at random from an ordinary deck of 52 cards. Find the probability of getting 2 aces if the first card is replaced before the second card is drawn. Okay, so part 8 is like sampling with replacements. Part B, the first card is not replaced before the second card is drawn. So this is like sampling without replacement. Alright, now what happened? Okay, so let's see, part 8. So, okay, the first round we have 4 8s, right? And how many cards total? 52 cards. That's the first round. And then the second round, we also have 4 8s because the original, the A's that you draw, you replace it back, you put it back. So that's why now for the second round, there are also 4 8s out of 52 cards. So that's why we get that. This is 1 over 13 times 1 over 13, so 1 over 169 is the probability. Part B. So if the first card is not replaced, okay, the first round we have 4 8s out of 52 cards. Second round, if we want to draw an ace, because you already have 1 8, so there are only 3 aces left, and then there are only 51 cards left. Okay, because we already draw 1 card. Okay, now what is this? Okay, this is 13. So we get 3 and 51. We can cancel. This is 7. Okay, so 13 times 17. What is that? 221. So 1 over 221. So this is the probability. Okay, and let me erase these so it does not look confusing to you. Okay, so this is the second round, and can you see they are different? Okay, so you can see they are different. So sampling with replacements or without replacements, the answers are different. And you can see 1 over 221 is not the same as 4 over 52 and times 4 over 52. So which means those when we sampled without replacements, we don't get independence. Okay, so independence is valid. When sampling without replacement. And because after you draw 1 card and you didn't replace, then your second round depends on the result of the first round. So that's why we don't have independence. Okay, let's continue. Example 6. About 13% of population is left-handed. If 2 people are randomly selected, what is the probability that both are left-handed? Okay, so that's why first people. The first people, the probability is 0.13, right? And also the second people, the probability is 0.13. So 0.13 times 0.13 is 0.0169. Okay? Alright, example 7. In a group of 100 people, 13 of them are left-handed. If 2 people are randomly selected, what is the probability that both are left-handed? Okay, the first one. We pick the first people. Okay, so we pick the first people. We have 13 of them and out of 100. Okay, but for the second people, what happened? Because you already picked one left-handed, there are only 12 left. Because you already picked one people, so now there are 99 people left. Okay, now you can see the second round, they are different. Alright, what is this? Well, let's see. Okay, let me move it here. 13 times 12. Divided by 9900. Okay, we get 13 over 825. That is the same as 0.015757. Okay, approximately equal to 0.0157, and then we have the 5 sevens repeated. Okay, so this is the answer. Note, please pay extra attention to the differences between example 6 and example 7. In example 6, the 2 events are independent because we just know 13% of the population is left-handed, right? So the 2 people you select are independent. But in example 7, the 2 events, the 2 people you select are dependent because we're picking from a group of 100 people, not the entire population. So we have a finite number of people right here. So that's why for the second people, the number you pick is already going to change. Okay, so they are dependent. So you can keep in mind, sampling with replacements, we get independence. The sampling without replacements, we're going to get dependence. Maybe let me write it down here. Okay, so sampling with replacement, we get the different rounds, they are independent. And then sampling without replacements, we get dependent. Okay. Alright, so let's continue in the next video. See you soon!